All right, so welcome to our first honors physical science or chemistry portion of Mr. McCune's Minute Science. This session right now is pretty much strictly for the honors class, but if anyone else would like to go through this and try it, it will be posted to all the Google Classrooms and to the main YouTube page so everyone can see this if they'd like to. Obviously, you guys have won the bet, as you just saw in the clip prior. I am fully mustached, hopefully just for another day or two, or else I don't know if my wife can handle it. But we are here to talk about polyatomic ions. And polyatomic ions are a pretty interesting thing that we haven't gone over yet, and they're definitely going to bring in some new concepts and some vocabulary that we need to understand and know. So at this point, we have done how to create an ion, what is an ion, what's the difference between a cation and anion, how do we do ionic bonding, how do the transfer of electrons work. We've worked all the way up through variable charges with transition metals, something like iron and lead that have multiple different charges. And now we're going to introduce one more topic in ionic bonding called polyatomic ions. Now, what exactly is a polyatomic ion? Well, a polyatomic ion is a group of atoms that have a charge. Poly meaning many, or a group or a clump. So different atoms are going to clump together, join together, and that clump itself will have either a positive or a negative charge, which it can then do ionic bonding with things that we're pretty familiar with. So we're going to put that up there. We're pretty familiar with things so far, such as sodium, 1+, magnesium, 2+, fluorine, 1-, or fluoride. So we are used to creating monatomic ions, where we just have one atom with one charge. And we've gone through all those processes, so we don't have to do that again, but we can just kind of showcase what we have done and what we have seen. We've also seen things like this. As I clear some of these away. We have seen variable charges, or one atom that can have multiple different charges or different varying amounts of electrons, called variable charges. We most commonly saw this in our transition metals, and we can see it here with iron Fe2+ and Fe3+. Whenever we worded those and put it into actual words, we said iron 2, iron 3 using Roman numerals. But to kind of go over where we've been and what we've done, we can look at a few different examples. And so we could take something like magnesium and fluoride, and we could bond these things together. We could add them together and create a compound. Magnesium having 2 valence electrons and fluoride having 7, or needing 1 and magnesium needing to get rid of 2 to stabilize that octet. So we look at the charges and we realize that they aren't quite balanced. Magnesium here has 2+, or 2 valence electrons in its outermost shell, where fluoride has 1-, or needing to gain 1 electron, because it only has 7 valence electrons, so needing 1 more to get to its full octet. Now, because these two charges, when immediately put together as MgF, don't balance out, and the overall goal of any type of bonding is to balance our charges out so we can become a neutral compound, we're going to need something else. And in this case, we would have drawn it out. We would have said Mg, we would have drawn the electron dot diagrams. Magnesium, having 2 valence electrons, was going to need to get rid of those 2, and if fluoride only had 1 available spot, then there needed to be another fluoride to occupy that last transferred electron. So we had 2 fluorides for every 1 magnesium. And when we look at this, we have MgF2, where we had 1 Mg and 2 fluorides. We named this magnesium fluoride. So now when we look at polyatomic ions, meaning a group of ions or a clump of atoms that group together and then have a charge, they'll kind of group like this. So there'll be a central atom that'll hold on to a few other ones that are really close and surrounding. They'll kind of bond together, and the bond they do is a covalent bond. And that's not something we've gone over yet as a physical science class, but we are going to be doing next week with covalent bonding. But just so we can see it a little bit, we are going to say the word covalent, which means to share electrons rather than to transfer, donate, or receive electrons. So they're going to be sharing the electrons in a general pool between them. Let's look at a few examples of polyatomic ions. I have 4 here, and on Google Classroom, I'll put a list of all the common polyatomic ions, things that you would regularly see and will be expected to know, especially as you move into higher level chemistry classes in high school. and beyond. So here we have 4 different polyatomic ions. As you can see, there are 2 elements, or 2 atoms in each one of these compounds, yet there's still a charge for each one of them. So we have hydroxide, manganate, phosphate, and ammonium. Some of those you guys might have heard before, and we're going to get a lot more comfortable with them as we do more practice, and we do some today as well. So again, they're showcasing a grouping of ions all together in a clump that possess one charge. And they'll behave just like any other monatomic ion when bonding ionically because, for example, phosphate is in need of 3 electrons to fill its full octet. So it's going to be looking for a partner, someone to give it 3 electrons. I'm going to keep ammonium out for right now. And we're going to put this one dead center. I'm going to get rid of our polyatomic definition. And we're just going to look at ammonium for a minute, just so we can kind of break this down and kind of see what is happening behind it so we don't have any further questions and we can kind of just get to solving or get to actually combining different polyatomic ions with monatomic ions. So when I look at NH4, ammonium, I can see that there's going to be a central atom, nitrogen, and there's also going to be these 4 surrounding atoms of hydrogen. And what I want to do is I want to figure out why does it have a 1+ charge? Because earlier in this video I said that the most important thing for ions to be doing is to be bonding together so they can neutralize their charge. Well, here we have 2 things that, well, 5 things exactly, that bonded together covalently yet still possess a charge, and we want to see why that is. So we have a breakdown. Here we have valence electrons, and we have the different atoms that make up ammonium. Nitrogen and 1, 2, 3, 4 hydrogens. How many valence electrons does nitrogen have? We can look at our periodic table up on the board, and nitrogen is going to say that it has 5 valence electrons. Each hydrogen only has 1. So in total, I have 5, 1, 1, 1, and 1. I get a total amount of valence electrons of 9 for ammonia. And now when we break that out, we can look at it in its actual molecule shape after it gets covalently bonded. Try to make room for all of my little posters. So here we have nitrogen in the center, just like in this video, or this picture here, where we had it. It's a central atom with 4 hydrogens around it. But this time I'm not going to draw circles around it. What I'm going to use is I'm going to take these valence electrons that we have already solved for, and I'm going to fill them in for our covalent bond. Again, don't worry so much about covalent bonding and how this is happening. Next week we'll go over this in more full detail. But polyatomic ions I wanted to introduce prior to going into covalence. So in total, we had 9 valence electrons. 9. That means we have 9 dots to put on our Lewis dot diagram here. And when we show covalence, we're showing a sharing of valence electrons. So there's going to be a pair between each one. So we have 9 total dots that we have to give out to achieve the octets that we were searching for. I know that nitrogen needs a full octet of 8 electrons to be happy. Hydrogen, however, being in the first group 1A, it only needs 2 electrons to be fully happy, to achieve that first complete energy shell. So I'm going to start giving some electrons in pair. So nitrogen and this hydrogen will share this pair of electrons in between them. It'll do so here too. There's 4 electrons, 5 and 6, 7 and 8. When I look at this picture right now, I can see that nitrogen has fully achieved its octet and is completely happy. However, looking at hydrogens, they're also happy. But what did I do wrong here? Or what did I leave out? It's 1 electron. I've only drawn 8 dots, yet I needed to draw 9. So there's this last electron that is kind of in this spot right here that isn't quite being used in any bonding. And so when this polyatomic ion forms, ammonium, NH4, there is 1 electron that still is just hanging out. And just like using sodium, for example, if I could find my sodium, there it is. And just like sodium had 1 extra electron. One electron that was just hanging on, and that's what gave it this 1+ charge, because it was able to donate that electron, then have more protons than it does have electrons, and gain a 1+ charge. Now for this polyatomic ion, because I have this one hanging electron, I can say that it acts just like sodium, where it needs to still get rid of that electron, and now it lets itself become a cation, where it can donate that electron to something like fluoride or chloride or oxygen. So what we show is we want to put brackets around this entire polyatomic ion. And we want to give it a charge, and because it only has one electron it needs to get rid of or donate, it's going to have a 1+ charge. So that shows us how a polyatomic ion gets its charge. Now what we want to do is we want to go up to the board and we want to do a few examples so we can kind of understand how to pair these up and then how to name them, because they are going to have a different structure than the last ones that we've done, especially when it comes to having multiple polyatomic ions. As you might tell, it gets a little confusing because we can have so many pieces. Let's head up to the board. All right, now we're back at the board here in our classroom. We want to kind of go over a few examples using polyatomic ions with other monatomic ions to create ionic compounds that are a little bit more than what we're used to. So we're going to have a lot more elements involved with these, but the process is just the same. It's just the memorization or the usage of polyatomic ions that you have to be able to kind of adapt with. You guys in Google Classroom will have a sheet of all the common polyatomic ions. There's a whole bunch of them. You're going to start to memorize a few of them the more you do practice with them, but we will have a set list where you can always go back to it and see it. Now, polyatomic ions, being a group or a cluster or a clump of atoms that all possess a specific charge, it's like that perfect pair, something like cookies and milk. These are fresh baked, by the way, just so you know. And when we look at two things such as calcium and silicate, we got one breakdown of what are these chemical formulas. And so we have calcium, Ca, and we have silicate, which is silicon, and oxygen. 3 oxygens. So now there's 4 atoms in this compound. It's bonded covalently, like we saw with NH4 and ammonium, and then we have calcium on its own, a monatomic ion. The charge of calcium, if I go look at my periodic table, is going to be in group 2A, or the alkaline earth metals, giving it a 2+ charge. When I look at silicate, the charge for silicate is going to be 2-. So we can go over that whole covalent bonding process again and see how many of those electrons are still needed, but silicate is going to need 2 more electrons. It needs to find some other element, or polyatomic ion, whatever it is, to give it 2 electrons. The charges match up, and we know from our other experience with ionic bonding that we don't need to do anything extra with this. And so when we finalize this, we say it's going to be calcium, silicate. That is our bonded ionic structure. That is a polyatomic with a monatomic. We still going to call this calcium, naming the cation first. And then we simply name the polyatomic ion as silicate. And now silicates are fond in my heart as a geologist, as there's a lot of rocks that are based on silicate minerals. So let's try another example. So I'm going to erase this. We're going to switch colors as black is starting to fail on me here. Let's take, for example, we'll start using blue. Let's take magnesium and hydroxide. So we're going to take magnesium plus hydroxide. Now, magnesium is Mg. It's also an alkaline earth metal, which means it's going to have a 2+ charge. And hydroxide, if we do the covalent pairing again, hydroxide is going to be oxygen, hydrogen, and it has a 1- charge. Well, we're going to have a little problem here because these charges don't match up. If we were to ionically pair these, we're definitely going to need more ingredients. We're going to need more OH. So when I go to bond these, I need definitely another OH. So I'm definitely going to need 2 OHs. But how do I write that as a chemical formula? Because it seems a little bit challenging at this point. So what we do when we have 2 OHs, we wouldn't just add a subscript to it. We wouldn't add a coefficient to it. Those are both things that we're not going to do. But instead, we're going to use parentheses to group that polyatomic ion together and then give it a subscript after that parentheses. So what we're going to be seeing is we're going to see magnesium only needing one magnesium, but needing two hydroxides. And so we use parentheses around the hydroxide, and then we use a subscript to indicate that there are two groups of that polyatomic ion. This 2 responds both to the H and to the O, not just to the H, which is what most people would think it would be. It's a lot different, because imagine if you didn't have the parentheses, you'd have MgOH2. In this case, this subscript of 2 is only going to the hydrogen. It tells me nothing about this oxygen right here. So let's get rid of some of the clutter so we have a final answer up there that we're very comfortable with. Getting rid of some clutter. We're going to have MgOH, but we need to put in parentheses, and any polyatomic that we're going to have multiple of needs to be in parentheses. And we're going to have 2 of them to balance out our charges. This is going to be called magnesium hydroxide. And I don't need to say anything about how many hydroxides I have, because in ionic bonding, there's no reason I need to say dihydroxide or double hydroxide. I don't need any prefix on it. I just need to remember that this polyatomic ion is called hydroxide. So I'm going to post up a little practice sheet for you guys in Google Classroom to kind of go over a few of these. You're more than welcome to reach out in the comments or send me an email personally or make a comment in Google Classroom, as some of you have done really well with so far. I'm happy to help. It's going to take some practice. Again, it's a little bit iffy, it's a little bit strange. This is our last ionic bonding concept before we really dive into covalent bonding. See you guys next time. See you.